In this session, we are going to build linked list from scratch. This is lead code problem 707, design linked list. Design your implementation of linked list. You can choose single linked list or doubly linked list. For sake of simplicity, normally it's better that we use single linked list. But here, for sake of learning, we are going to use doubly linked list. Then comes the definition of the node with the linked list. A node in the single linked list should have two attributes, val and next. Val is the value of the current node and next is a pointer or reference to the next node. In case of a doubly linked list, we have val, which is the value of the data in the linked list node, next, which is a pointer to the next node, and then a previous pointer to the previous node. If you want to understand doubly linked list, you will need to have one more attribute previous to indicate the previous node in the linked list, just as I said before. Assume all nodes in the linked list are zero index. So this is going to be designed on lines of array. Then comes the function signatures associated with linked list operations. We are going to build an object myLinkList, and the object instantiation is done by myLinkList construct. MyLinkList function initializes the myLinkList object. Then comes bunch of operations. So we're going to have get. The get function takes a parameter int index, get the value of the index node in the linked list. If index is invalid, it returns -1. And get function takes one parameter, which is integer value, attempts to add a node to the value before the first element of the linked list. After the insertion of the new node will be the first node of the linked list. Then comes add a tail. That also takes the integer value and appends a node to the end of the linked list, which is in fact that turns out to be the last element. Then comes add at index. It has two input parameters, index and value. The goal is to add the value of a given index. Add a node of value val before the index node in the linked list. If int is equal to length of the linked list, the node will be appended to the end of the linked list. If the index is greater than the length of the linked list, the node will not be inserted. Finally, we have deleted index. The node at a given index will be required to be deleted. Delete the index node in the linked list if index is valid. So these are the bunch of functions that need to be constructed or built. And here is an example. The example performs some linked list operations, including instantiation of the linked list object by calling myLinkList. And then performs addition of a node to the head of the linked list, then to the tail of the linked list, and then at a given position or index, it performs a fetch or a get operation, also performs delete at a given index, and then these are operations. The constraints are given like this. The index is between 0 and 1000. The value is also between 0 and 1000. So that should not matter to us much because we are going to use default metadata. Please do not use the built-in linked list library. So basically it needs to be built from scratch without using any license. At most, 2000 calls to be made on each of these linked list operations. With this background, we'll go ahead and build this. Now I'm going to reduce the window size and focus on the code. So I'm going to exit this description and shrink up the windows. So here you see a bit of code previously that we had built for designing single linked list from scratch. Our goal now is to build doubly linked list. So we'll need to modify some of these implementations and introduce additional manipulations to the new field that we are going to add to the node structure. The new field that we are going to add typically looks like this. So it's going to be a pointer to the previous node also. So this is going to be a definition for doubly linked list. Okay, so with all that, let us get started. I'm just going to retain some of these pieces so it becomes repetitive and then going to reset this implementation so we build it from scratch. Okay, we have reset everything. I'm now going to say implement doubly linked list from scratch. Going to paste the piece of code that I had pulled out from the previous implementation over here and build on top of it. Definition of doubly linked list, we have a node structure defined here. It takes data value val, which is of type integer. It could be any data type. And then next is a pointer to the next node in the linked list. It links the current node with the next node. And then here we have a previous pointer which links the current node to the previous node. For the head node, the previous node will be nil, and for the tail node, the next node will be nil. So that's by definition. So we'll need to define the hook to the head, and we could think of a linked list something like this. So the definition of the hook will also hold the tail point. The length of the linked list is being tracked, and therefore we'll need to update the length of the linked list every time we go ahead and add a node to the head of the linked list or at a given end, and then increment length. So these are the two basic objects that we will manipulate throughout our linked list operations. Let me go ahead and further minimize this so that we simply straight focus on our implementation. We are now going to begin with building the constructor. Constructor to my linked list object will return a my linked list object, and previous implementation for single linked list had only two parameters that need to be returned, but here we are going to have three because by definition of my linked list objects we have head, tail, and length. So head is nil, tail is also nil initially, and then the length is also going to be 0. So here goes the constructor definition. This shows the pictorial representation of a doubly linked list. The head node of the doubly linked list is here at 5. This is the first node of the doubly linked list. The tail node is at 1, which is the last node of the doubly linked list. Each node in a doubly linked list comprises of the value pointer to the next element and then a pointer to the previous element in the linked list. Here, as you see, there is the next pointer and the previous pointer held by each node in the doubly linked list. The next pointer of the last node is nil, and the previous pointer of the first node is nil. Initially, the linked list is empty and both head and tail points to nil. These are a bunch of elements that we are going to insert into the linked list at its head. So we have 1, 7, 6, and 5 as new node, and each one of them holding its current value as well as next pointer currently pointing to nil. We need to link them. Let's do it right away. We'll now insert, that's going to be the new node that's going to be inserted at the head. The next pointer is going to be nil, and because the list is empty, both head and tail pointing to nil, we will require to move both head and tail point to the new node. Now, new node becomes the head and new node also becomes the tail. The next node is nil, so is the previous node also. Next, we are required to insert 7 to the head. So let's move this here and then position it accordingly. So we are required to move it to the head. So we need to make head of previous as 7 and new node of next as head. So we just move this accordingly. We make this nil here. The head of previous will become 7, which is a new node, and new node of next is going to be. So now we change head pointer new node. So now head changes. The tail, however, remains at the same position. So let's keep it as is. Just going to reposition this, make it look bit and provide more space for addition of the rest of the nodes to the list. Likewise, if we were to insert new node 6 to the head, we bring it over here and then move the head pointer currently at 7 over here and then position it accordingly such that the next of new node is the previous head and new node becomes head. Finally, we have one more element that needs to be inserted at the head, which is 5. We change that here and make head of previous as the current new node. You see here, when the new node of next becomes this, we further change the position of head to new node. And we are done with implementing addition of new nodes to the empty linked list. Let us go ahead and implement it. What we see here is duplicate of the constructor and the linked list object. So I'm just going to remove it because we have already created over here. So now this is the get function, which we will defer implementation to a later stage because we first need to insert the element into the linked list. So let us move it here, somewhere here. We'll look at it later. Now I'm going to add new elements to the head. So add new elements to the head of the list. So first thing, as we saw in our visual representation, is to create a new node with value val. So let's do that. New node colon equal to address of node, and that's going to hold val as val. That's going to come as an input parameter here. So this is the input parameter, and this val is this val that we are going to assign it. The next and the previous pointers are initially nil. We could initialize that here. I want to say next is going to be this dot, right? And previous can be, I can leave it empty also. So we are done with creating new node, creating a new node with input value, input value. Now we need position this new node into the head accordingly as we had seen over the visual walkthrough. If list is empty, a new node becomes the head. So if list is empty, new node is the head. So this dot head equal to new node. And if list is not empty, let's do that here. If this dot head not equal to nil, which means list is not empty and it already has few elements, then the previous node of the head becomes the new node. So this dot head dot previous equal to new node. We need to handle the tail. If this dot tail equal to nil, which means the list was initially empty, and if that is the case, then this dot tail equal to, and if list is not empty, we don't modify the, we just keep modifying the part dependent current list. Now we also need to update the value of len by incrementing it by 1. So this is the implementation of adding an element to the head of the len list. Now, if we are required to add a node to the tail of the linked list, we will modify tail's next pointer point to the new node. Consider 4 new nodes here. So we have each node holding its value and pointer to the next node and with a pointer to the previous node also. Initially, the linked list is going to be empty with both head and tail pointing to new. So let's keep it both of them pointing to nil. So now if I am required to insert element 1 into the linked list which is empty towards its tail, I will create a new node 1 and then make head and tail point to the new node because tail is currently empty. So I'm just going to make it point to new node. So this is going to be nil. The new node's previous node is going to be nil. The new node's next pointer is also going to be nil. If I am required to add node 7, which is a new node, to the tail of the list, then tails next is going to be the new node. So I'm just going to place this over here such that tails next node becomes new node and new node's previous node becomes the tail. So now I need to change the position of tail to the new node. Likewise, I can go ahead and insert node number 6 also to the tail. So that's going to position 6 previous node as tail and tail's next node as 6. So that's going to be here. Finally, we have element 5, which is also going to be positioned in the same manner. So it's going to be like. So we have built the linked list completely by addition of node to the tail. So we have 1767. It is in the order in which we have been adding nodes to the tail as 1, 7, 6, and 5. And in case if we had added 5 to the empty list initially, letter 6 and 7 and then 1, it would have resulted throughout within a past here. With this background, let's go ahead and implement addition of node to the. Next, we implement addition of a node to the tail. So here it goes. Add a node to the tail of the list. So as we know, we create a new node that is going to be node with value val comes as an input parameter. And here we are going to add the node to the tail, and therefore we update the previous and next pointers accordingly. The previous is going to be this dot tail and head is going to be nil. Okay. For addition of node to the tail, we always manipulate the next pointer of tail, retain the head as is, and process. So if tail was pointing to nil or if linked list is initially empty, we make tail as the new node. So this dot tail equal to new node. However, if tail was not nil, if list is not empty, so basically if this dot tail not equal to nil, then this dot tail dot next will be the new node. If list is empty, tail becomes the new node. Now we process the head if list was empty. If list is not empty, we do not touch the head. We just keep adding elements only to the tail. So if this dot head equals to nil, then the new node itself becomes the head. That's it. We increment the size of the linked list by 1 by updating when variable. That's it. So this goes with implementing addition of a node to the tail. Now for addition of a node at a given index, consider a linked list, list A as you see here. It's a doubly linked list. There are 4 elements and the head node is pointing at index 0. We know it's going to be beginning with 0 index. There are 4 elements and therefore the last index is 3, which is the tail node. We are required to insert a new node that has value 5 with previous and next pointers defined at index 3. Now, to insert this, we introduce a new curve point and we point that to index 0. We walk curve pointer until index. So let us walk now. When we hit index, we bring in this new node for insertion such that pointers of new node and the pointers between index and index minus 1 gets aligned. So I'm going to move this over here and demonstrate the same. Now we had initialized new node such that new node of previous becomes car of previous and new node of next becomes further that previous dot next becomes new node So basically we turn like this and color previous becomes new node. So we change the position like this. So with this implementation, we have new node inserted between index 2 and index 3, and therefore we have this index modified as 4 and new node at given index 3. So we've been successfully able to insert new node at index 3. Let me realign this to make it look correct. Yes, this becomes new node at index 3. With this background, let us go ahead and implement it. The next one is addition of a node at a given index. So we have an index or a position along the linked list. So that if there are two elements across the linked list, and if we are required to insert an element at position say n by 2, then we need to walk until n by 2 and insert the new node. So let's see how it can be implemented. This is about inserting node at a given index or position. The algorithm goes something like this. We'll follow the steps one by one. So initially, we'll find out if index is out of range. We need to perform some sanity checks. So this is about performing sanity. So check if index is out of range. Then we check if uh, index is 0. Check if index is 0. If index is 0, then it means we are going to add the node to the head of the list. So I'm also going to comment it here. If index equal to 0, add new node to the head of the list. Next, again we perform sanity to check if index is equal to length of the list. So check if index is equal to length of the list. If index is equal to length of the list, it means that we are going to add the element to the tail of the list. So index equal to length of list, then add new node to the tail of the list. After performing all this sanity check, if index is not matching any of these conditions, then it means that needs to be inserted somewhere in the mid. So now we are going to initialize the curve pointer at head and walk towards the index. Then create a new node with value equal to val previous pointing to cur.previous and next pointing to finally perform the insert operation, insertion of the new node between index and index minus 1 position, and then simply run. So with this algorithmic approach, let us go ahead and fill up our code. So here if index is lesser than 0 or if index is greater than this dot length, it means index is invalid or out of range. We simply return. Here if index is 0 we are expected to insert the new value at head. So we simply call this dot add at head, which we have just before created with value and then return. This is when index is equal to len of list. So when index is equal to len of list, we are required to add the new node to the tail of the list. So we are simply going to call the function that we created to insert a new node into the tail of the list. So if index is equal to this dot len, then this dot add at tail is the function that we created, add the node at the tail, and we return. Now, if it is none of these, then we are required to insert the new node at a given index somewhere in between the list. So for that, we will set the current pointer at head position. That's going to be this dot head. And then we'll walk towards index. So we will walk towards index with the for loop I less than index I plus plus. We take one step at a time. So cur equal to cur dot. Now at this position, once we are done with walking towards the index, we are good to create a new node. So we'll say new node colon equal to ampersand of my linked list that we had initially called out here, going to be here. So we're going to create a node for the my linked list structure. So that's going to be val colon val previous equal to cur dot previous and next equal to cur. So initialization is with colon. We have created the new node. Now we are good. Go ahead and insert it. So to insert it, we need to change the cur pointers. Cur dot previous dot next equal to new node. Just as we had witnessed during the visual walkthrough, I am changing the pointers of cur pointer equal to new node. Now before I return, I'll have to update the len variable, which is part of my linked list object. So this dot len plus plus that could be increment length of the list because we have successfully made an update by inserting a new node into the given index. And now good to return. With this, we are done with implementation of a new node addition at a given index. Next, we are left with two more functions, which is delete at a given index and then function we will go to write. We are now good to implement that function because if we were to assume addition of nodes to the linked list at the beginning, at the tail, or at the given index, we have accomplished that and we know the logic behind performing. So now let us get the function because we assume that there are some elements in the list. So get this fetch the value of the node at a given index. So the get function takes an input parameter index of type integer and it returns the value at a given index. which is integer again. We need to perform some sanity check to see if index is out of range, just as we did with previous code where we inserted a node at a given index. Sanity check will include to see if index is lesser than 0 or index is greater than this dot line. And if it is so, it is out of range. So we simply return. We cannot retrieve any value from out of range index. And this call expects an integer value return. So we are going to return -1. Now, to retrieve the value at a given index, we need to have a card pointer set at head. And then we are going to walk towards index. And when we hit index, we are going to pull out the node's value at the given index and return that. That is as simple as it. So let us initialize curve to this dot head, initialize a walker, which is curve, and walk towards the index. So now I'm going to walk towards the index with help of a for loop. I less than index, I plus plus, take walker at one step at a time. So we are done with walking towards the index. And when we have reached the index, when here we have reached the index, here we are at the given index with the walker. Walker here is cut. So we have the value, which is car.val, and we return val. This is implementation of get function or fetch function for a given index on a linked list. Consider this linked list with four nodes where we have head pointing to index 0 and tail pointing to index 3. We have head at node with value 5 and tail at node with value 1. There are three cases that we can consider for deletion of a node at a given index. Case number 1 is delete at index 0. If index is 0, then we have index 0 here, head pointing to 0. All that we are required to do is just change the position of head such that the head automatically gets deleted. So now the linked list becomes 6, 7, and I put this back now. And if in case 2, we are required to delete node at index 3, then all that we are required to do is move the tail pointer to the previous node of the tail, and therefore the node at index 3 or tail gets automatically deleted. Now, case 3 is the case where we have required to delete a node at index 2. That is, we are required to delete. I'm just going to mark it as a special case. Now, in this case, we will be using a curve pointer. So I'm just going to call upon a pointer here, declare it as curve. So we're going to walk curve until index, take one step at a time and walk until here, and then change the previous and next pointers of curve accordingly. So I'm going to just change previous over here to point it to the next node of curve and the next pointer of this change over here. So now We have 6 connecting to 1 instead of 7, and therefore node 7 is automatically ready. That's it. With this visual walkthrough, we can jump into our implementation. So now the last thing that we are going to build with defining the linked list is delete a node at a given index. The deleted node at given index takes a parameter index, which is an integer value, and we are required to delete the node at the given index. So let's go ahead and build it right away. So the first thing that we need to do is perform some sanity check. We need to check if the index is within the given range. If it's out of range, we do nothing. So index should not be lesser than 0 and should not be greater than length of the list, and if so, it is out of range. We'll perform the sanity check right away. Sanity check on the index. If index is lesser than 0 or index is greater than this dot len is the length of the linked list that we have been accumulating so far when we are adding nodes. If that is the case, we simply return. We don't perform any deletion. Now we set the current pointer at head, this dot head, and then walk towards the index. So I'm going to add a comment here. Set the walker or curve as a current pointer and walk towards the index. We are going to set the walker to head. So to walk towards the index, I'm going to make use of a for loop as usual. I less than index I plus plus, and then take one step at a time and walk the walker. That is the current part. Okay. So now when we are done with this, we have three conditions. We could have index at 0, which means we are required to remove the head node. We could have index at length of the list, which means we are required to remove the tail node. Or we could have the index somewhere in between, and we could be required to remove that particular node at a given index. We need to handle these three cases. To handle that, we are going to introduce some executor. So let's do one by one. If index is equal to 0, then this dot head is going to be per dot. So basically, we are skipping the current head and making the next pointer as new head. Otherwise, current dot previous dot next equal to current dot next. Otherwise, just hop a node. So basically, we are hopping the node here. Here, we are removing the head. So this is case 1 and case. Now there is case 3. That is case 3 and case 2. If index equal to this dot len, then this dot tail equal to cur dot previous. Basically, we are removing the tail node. Otherwise, we are going to modify the next pointer cur dot next dot previous equal to current dot previous. So basically, we are modifying the pointers accordingly. And finally, increment the length. So if you remember, we were incrementing the length, we were adding nodes to the list. Now we are going to decrement the length of the list. This dot length minus. So, so we are done with the implementation. We perform a quick sanity check and should be good. We will now perform sanity check and then take a run. The struct node definition looks good. The linked list definition also looks good. Constructor is fine. Takes nil, nil, and 0. That corresponds to head, tail, and len. Fine. Now we have added head, creation of the node. All right. Good. Perfect. Added tail. I see a typo here. This needs to be curly braces. This is not head. This is next. Okay. There is a typo here also. Okay. Rest of it looks good. Add at the given index. If index is less than 0, or there's no need for another if. Okay. Cur needs to be initialized here. Look good. This needs to be uppercase val. All right. Even here, this needs to be initialized. CURR typo. Delete at a given index. Looks good. Okay. Perfect. We'll keep our fingers crossed. A pretty big phone. So chances of errors slightly high, though we have performed sanity check. I'll take a good chance and run it. Hopefully there are no compile errors. We have a test case. That's one test case which we have walked through here during explanation. Okay, let me check fair chance and run it. Wow, perfect. We had missed the single error, could have just halted. All right, looks good. We could go ahead and submit it to let it run through multiple test cases, particularly address the corner case. But before we submit, I see a potential correction required here when index equal to len. So we need to check if index equal to len minus 1 because we are starting at 0th index. So if it is a tail that needs to be removed, then we need to see if it is len minus 1. And also the range needs to be if index is lesser than 0 and if index is not just greater than len but also equal to len, it is out of range. So we did check this in one another place. That's here. The reason why we need to check len minus 1 is because it started 0th index and then ends at index 3 for a list that's holding 4 nodes. With this clarity, we can go ahead and print. So now the runtime and the memory consumption looks really good. We are done with implementing linked list using doubly linked list from scratch.